change of sign and why the critical points method works so well. It's basically this: a function is only going to change sign from positive to negative at an x-intercept or at a discontinuity. And there's no way you can move along a curve and go from negative to positive without passing through the axis. The only other case would be something like our hyperbola there. Our hyperbola there, where we've got that asymptote. So okay, then it can change from positive to negative. But they're the only two situations. So that's how we can find these critical points. And why they're so important, because that's where it will change from positive to negative. If I have to solve an inequation like this, well, what's it actually saying? If I think of that curve, I know I'm going to have a double root at 1, a single root at -3. It'll look something like that. Again, I'm not overly concerned about the y values, just the x values. We're saying, when is that curve below or on the axis itself? Well, it's those 2 points is when it's on the axis. We want to know, when is it below for that section there. So less than or equal to -3, but not forgetting x equals 1. A lot of people will forget x equals 1 on that one because it's just that single point, but it is still part of the solution. So back to this sort of inequation then. This idea, what I can do is I'll pull the 5 over to the left hand side but write it as one algebraic fraction. And then I can use the idea, well, it's got to be either an x-intercept or a discontinuity. Well, the x-intercept or the zeros, fraction equaling 0, it's got to be the top of the fraction. So I just solve the top of the fraction equals 0. I get x equals -13 on 5. Discontinuity, well, that's the bottom of the fraction can't equal 0. And that gets the other one, -3. I've got my critical points, the same as before. We test some regions and we get the answer. So that's another way of doing it. Create an algebraic fraction, just look at when's the top of the fraction equal to 0, when's the bottom of the fraction equal to 0. Here's one from last year's HSC. And this is why this obsession with multiplying by the square is not that great. This one here, 1 over the absolute value of x minus 5. They gave us that graph. And then they said, solve this. X over 6 is greater than or equal to 1 over the absolute value of x minus 5. Well, I know x can't equal 5, and the graph sort of confirms that, because that's a graph of that one. Let's solve the equation. It's an absolute value equation. So either the positive of the x minus 5 on the bottom there, or the negative of the x minus 5. On the left hand side, I get two possibilities there, -1 and 6, and on the right hand side I get 2 and 3. So I plot all of those critical points I've now found, right? And there's 5 of them. But I know -1 is not a solution. I can discount that straight away, because go back to the original question. I'd end up saying the absolute value is equal to a negative number. Well, that can't happen. So that's why I circled that -1. I know it's not part of the solution. The other ones, well, 5 was an exclusion because of the bottom of the fraction, so I didn't include that one. But the other 3 critical points are included. Now, what's this question saying? When is x on 6 equal to that? I can use the graph they gave me to test the critical points rather than substituting in. So if I draw in the line y equals x on 6, you'll notice we've got some points of intersection, and they correspond to those critical points. So there's x equals 2, 3, there's 5, which wasn't included, and 6. And so all I'm really now saying is, when is that line above the curve? And so in between 2 and 3, but also when it's bigger than 6. So there's my solution. Okay, we'll add 5b.